Scientists wish to relate pressure, definitely, as well as volume and amount, which will be moles, and temperature to gases. And there's many different ways to do this, but what's usually used is what's called the ideal gas law. And the ideal gas law is just a great way that sums up all the different changes that you might experience while studying gases. So when it comes to any sample of gas, this could be water vapor or methane, natural gas, carbon dioxide, etc. You have to consider the pressure of the gas, the volume of the gas, the temperature of the gas, and definitely how much gas you have, which scientists will use the mole. Now, here are some units that are going to be super helpful in this section we're getting into. For pressure, once again, 760 millimeters of mercury equals 1,013 millibar, which equals 1 atmosphere. They're all the same. And also a millimeter of mercury and a torr are the same thing, so you can interchange those units. For volume, 1,000 milliliters equals a liter is going to be very, very helpful to us. And remember that a milliliter and a centimeter cubed are the same thing, so we'll go back and forth between those. We're going to interchange Celsius to Kelvin in temperature a lot. You add 273.15 to the Celsius temperature to get the Kelvin temperature. And then finally, we will talk about the moles of gas. A lot of times you'll need the molar mass of the gas. So from the periodic table, you can find the grams per mole of, say, helium, or the grams per mole of, say, water. You can turn the grams into moles and be good to go. Guy Lussac, I may be totally mispronouncing that name, and I apologize to that scientist. But anyway, he was the one that figured out that there's a temperature dependence on the pressure of a gas. And if you use Kelvin temperature, and you must use Kelvin, then the pressure is proportional to the temperature. So as the temperature goes up, the pressure goes up. And as the temperature goes down, the pressure goes down. Now, Kelvin is the ultimate way to use this law, and I highly recommend that in this section you always convert any Celsius things you see into Kelvin. Celsius values can be negative and 0, so that's why we have some problems with the math. But anyway, you can see there, even though that pressure is in kilopascals and not atmospheres, you can see that as temperature goes up, i.e. go down the column, then the pressure goes up as well. This is the idea. The K value there is a constant. So what scientists will do is they'll have two sets of conditions, a pressure 1 and a temperature 1, and then a pressure 2 and a temperature 2. And when you figure it out, P1 over T1 equals P2 over T2. You can graph pressure versus temperature, and that graph in the lower right there, it's a nice linear line, which is kind of cool. Oh yeah.
Temperature and volume are directly related. As heat is added to a sealed syringe, the volume of the air in the syringe increases. A plot of gas temperature and volume demonstrates that the relationship between them is linear. If we extrapolate the line down to a temperature of absolute 0, in principle, the gas has no volume.
Charles' law. Charles was another scientist that did work a long time ago on different gases. But anyway, Charles's law relates volume to temperature. And just like with pressure, as the temperature goes up, the volume will increase. And as the temperature goes down, the volume will go down. And like with pressure, you can get the V1 over T1 equals V2 over T2 expression, which is really cool. So this is Charles' law. And by the way, you don't need to know the names of these scientists, but of course, the mathematical relationships of all these will be important. So I won't ask you like what's Charles' law or what's Guy Lussac's law, but I will ask you questions about volume and temperature, pressure and temperature, stuff like that. One interesting thing about Charles' law is that if you extrapolate that data all the way back to 0 Kelvin, which is absolute 0, you can see how in theory the volume of the gas goes to 0. And as long as you have atoms, which have mass, all right, you're never going to get truly to 0. So some strange things start happening when you get to really low temperatures. We'll briefly talk about that here in a little bit. But under normal conditions, i.e. temperatures that we're used to, Charles's law, as well as Guy Lussac's law, works really well. One fun thing about Charles's law is liquid nitrogen, and you can take, for example, a balloon, which has a normal volume, place it in the liquid nitrogen, which is very, very cold at 77 Kelvin, which is minus 196 Celsius, and the volume goes way down. So remember, we're going from a warm temperature to a very cold temperature. Temperature goes down, the volume goes down, and you can see that balloon there. When you take it out of the liquid nitrogen, it's really shrunk down. If you let it sit around on the desktop for a while and warm up, it goes back to its normal volume, which is kind of fun. Charles basically studied balloons to figure out all these laws, which is cool. He was really interested in flying machines, the balloon especially, and stuff. He's a fascinating person to read more about if that's anything you're interested in. So here's a question you might see. The volume of a gas is 235 milliliters at 25 degrees Celsius. At what temperature would the same gas have a volume of 310 milliliters? And we'll assume, by the way, that the pressure and the amount of the gas are constant, and there's 5 different temperatures there. Okay, the one tricky thing about this is that we have 2 volumes, and that's not a problem. But again, notice that it's in Celsius, and if you're going to make use of these kind of laws, you must convert things to Kelvin. All right, I'm just letting you know right now. So in this section, if you see a Celsius temperature and it asks about pressure or volume or whatever, convert over to Kelvin. So in this problem, first thing you'll do, 25 Celsius plus 273 will give you 298 Kelvin. That's the starting temperature here. You don't want to use Celsius. And then you can use V1 over T1 equals V2 over T2. So you'd solve for T2 in this case, but the temperature that's going to come out will be in Kelvin. So you have to then reconvert the Kelvin back into Celsius here to make sense of this answer. So if you do all that, you can see that first of all, I turned 25 Celsius into Kelvin, 298 Kelvin, no problem. Then the answer that came out was 393, but it's not Celsius, it's Kelvin. So if you subtract then 273 from 393, you'll get 120 with a dot showing 3 sig figs. That's going to be the temperature and stuff, where the volumes would be then 310 milliliters.
Pressure and volume are inversely related. Weight on the plunger of a sealed syringe increases the pressure on the air in the syringe. The air cannot escape, but its volume reduces under the pressure.
This is Boyle's law. Boyle was another scientist. Again, look at those dates. Wow, like 1600s, man. Just absolutely crazy. But Boyle studied pressure and volume. And what basically Boyle came up with is that the pressure times volume for one set of conditions equals the pressure times volume of a second set of conditions. So it's a little bit different. Scientists call this an inverse relationship. As one goes up, the other one goes down. So for example, if you increase the pressure, then the volume will decrease. On the other hand, if you shrink the volume down, lower the volume, then the pressure would go up, etc., etc. So notice that in the 2 graphs at the bottom, if you plot just regular volume versus pressure, it's a curve. And curved things aren't as easy to predict as linear things. So if you change the volume versus pressure to volume versus 1 over pressure, then you get a nice line. And you can predict that way quite accurately what's going on. So Boyle's law is pretty cool for predicting different things like this.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
Avogadro, of Avogadro's number, actually predicted that there would be some amount that was used, which is now called Avogadro's number. But he didn't actually calculate the number. He did realize from the study of gases that the volume of the gas does depend on the amount of gas. And so this video that we just showed on the right-hand side is awesome. It shows the reaction where water is being formed, and you can see the stoichiometry. 2 H2 are needed for 1 O2 to make 2 water. So initially, the H2, the circle, is bigger than the O2 because you need twice as many H2s, so the volume will be twice as big. The moles is proportional to the volume. But in that video, initially, when the 2H2 and the O2 were combined to make 3 moles of gas, the circle was even bigger. So you can see here how the volume is proportional to the moles or molecules. So mathematically, volume is proportional to the moles. So as moles goes up, the volume goes up, and as moles goes down, the volume goes down. So what you can say then from this equation is that V1 over N1 equals V2 over N2. So it is the amount moles N changes, then the volume changes, and that's kind of cool. We're also going to see though that volume is proportional to the amount that's there, and there's actually different numbers. On the right hand side there, we've got 2 tanks with helium, and on the left hand side we have 1 mole of helium, and you can see the balloon is normal sized, I guess. If you have twice as much helium, which is what we see on the right hand side, the balloon should be twice as big. So as moles goes up, the volume goes up, and vice versa. Pretty cool. If you combine pressure, volume, and temperature into one expression, you end up with what's called the combined gas law, and it's pretty handy. Now, P1 V1 over T1 equals P2 V2 over T2. So if pressure, volume, and the temperature are all changing, then you can use this expression. Now, you must use Kelvin for temperatures, definitely, but this is a nice way when you have more than one type of gas unit that's being changed at one time. If you also have moles that change, then you can use P1 V1 over N1 T1 equals P2 V2 over N2 T2. So again, lots and lots of different perturbations here. Just depends on which one you actually use. So wow, there's a lot of expressions, all right? You can see there's Guy-Lussac's law, and there's Charles' law, and Boyle's, and Avogadro's, and combined gas law, stuff like that. And I get kind of like, oh, like that person gets kind of fuzzy. I don't quite know which one to use. So I'll just let you know that the one that I use almost all the time is the one on the next slide, and it just combines all these other laws into one. You can use it to find these other laws we've talked about if you need it. So let's talk about the one that I use all the time.